Hi, Chem 2. This is about vapor pressure. This is in Chapter 11, something that I was going to cover officially in a lecture, but I'm not going to. I'm going to have you guys review it here. But let's talk about what vapor pressure is. This is actually one of these things where the definition of, or the word is the definition, essentially. It is the pressure caused by the creation of a vapor. Now, okay, great. How do you create a vapor? Where are you actually getting this vapor from? Well, hopefully the picture that you see right there is a little indicator as to where it's coming from. So, okay, so in here I have a beaker of water. Now, on the surface of the water, we have water molecules. Actually, of course, we have water molecules everywhere. I'm just going to draw them as little particle balls. And of course, remember, these are all being held together. One, there's two things. Atmospheric pressure is holding them all down, or essentially holding, using gravity to help hold everything down. But the other thing, what's going on in here, are the attractions that's holding those water molecules together. And of course, what attractions are we talking about with water, which is H2O? Okay, remember you end up having a water looks like that. We can form two dipoles going that way. Oxygen has an electronegativity of 3.5. That's very large in comparison to hydrogen. So this is we get hydrogen bonding, or like I like to call super duper dipole forces. So that's what's holding these molecules together. However, there's also, remember, atmospheric pressure. Remember, we all have atmospheric pressure pushing down on us. So between those two things, we end up having our water end up staying in our flask. Okay? Now, but there's always a few of these water molecules. There's always a couple that get enough kinetic energy in them that they evaporate, meaning they become a gas. So you always have a few that become a gas, the ones with higher kinetic energy. So in these cases, the kinetic energy is winning out over the attractions. Okay? So if you form enough of these molecules, or any whatsoever, you actually end up forming a opposite pressure. You have atmospheric going down. This forms a pressure going up. And that's the pressure of these molecules trying to escape their liquid, confines, and they want to go and escape and be free. Now, so you have these two opposing forces, and so this is what's known as vapor pressure, is this pressure that's being formed by this evaporation. Okay, great. So we just talked about water. Now, how can we can actually adjust this vapor pressure if atmospheric pressure stays the same? We'll just say we're at 1 atmosphere here. How can we adjust the vapor pressure? How can we get more of these molecules to become a gas? Well, we could. That's fire, by the way, if you can't tell. What could we do to our flask? We could heat it, because if we heat it, what happens to the particles? They start moving faster, the kinetic energy goes up, so that means it's actually fighting against the attractions, so you would have more and more and more of these molecules becoming a vapor. So that means the vapor pressure is going to become bigger and bigger and bigger. And once you finally get to the point where your vapor pressure, okay, that's one big arrow going up, when your vapor pressure equals the atmospheric pressure, there's nothing else now that's holding those liquid molecules behind. They can all become gas. And what happens when they can all become a gas? This point is your boiling point. Okay, so that's actually technically what boiling is. It's when the atmospheric pressure equals the vapor pressure. That's what the definition of boiling point. So if you have something like water at 1 atmosphere, it's going to take a certain amount of heat in order to get that to boil. But the temperature, we already know. What temperature is it going to need to get to? What's the kinetic energy going to have to be in order to get this all to boil? 100 degrees Celsius. So once we get it to 100 degrees Celsius, then we know that the vapor pressure created by the water is equal to the atmospheric pressure, so it boils. Okay, so now how can we adjust this? Well, we can always adjust it by, let's say instead of water, let's say we have a liquid that's more like acetone. Acetone looks something like this, the molecule. Lots of CH's, one double bond, and looks like that. So when it comes to our intermolecular forces, because we have so much of the carbon-hydrogen bonding, that's going to lead to LDFs, which we know are the weakest. And then we may get a little bit of dipole forces here, but nothing quite as strong as hydrogen bonding. So acetone is going to have a lower boiling point because it's going to take, there's atmospheric pressure again, holding everything down. It's going to take less energy to get these to become a vapor. Why? Because there's fewer attractions. Okay, fewer attractions, so less kinetic energy needing for this to meet the vapor pressure, so it actually has a lower boiling point than something like water, which is 100. Okay. Another way you can kind of fiddle with vapor pressure. Let's go back to water. We got water in here. Let's say we take this and we close the lid. Okay, so, and then we're going to, here's our water, forming a vapor pressure, but then we're going to heat it up again, which is going to form more and more and more and more and more. But the pressure, because we're adding more vapor to the air, the pressure is increasing. So that's essentially, no longer do we have atmospheric pressure at 1 atmosphere, essentially. We have this increasing pressure. So what ends up happening with the increasing pressure, it's going to take even more of these molecules to meet it because it's actually increasing the pressure that it's making. And so the boiling point of something like this, in this situation, is going to increase because you're going to need to add more and more and more heat in order to counteract all of this pressure that's on the inside of this container. Does anybody know how this works or what this commonly is known as? This is a pressure cooker. A pressure cooker, you might know, is one of these, maybe your grandmother has one or great-grandmother, and it's one of these big metal pans that lock down and have this little thing on the top that go Anyway, that's how this works, is if you increase the pressure on the inside, then you end up, can you increase the boiling point? Because again, it's going to take more kinetic energy in order for it to equal the pressure on the inside to boil. In fact, it's very hard to get it to boil. And so you can increase the boiling point. If you increase the boiling point, instead of water boiling at 100, it'll boil at something, say, like 130, which ends up if you have food down in here, it will cook your food faster. So that's why pressure cookers are used. Anyway, so that's a little bit about vapor pressure. We're going to come back to this in a bit, but that's it. Thanks.